have set their times they want to take the test. You'll have an hour and 45 minutes, and it is, like I said yesterday, kind of a challenging exam. If you know your stuff well, I think you can finish in an hour and 15 or so, but if you don't know it so well, it might take closer to an hour and 45. So study well, study those problems. I'm going to do my best to do a real thorough review today, though I do need to talk a little bit about some new stuff that's on the supplementary videos related to masses on springs and PredatorPrey models. That's the new stuff on the exam. You're not going to have anything to turn in on Friday. I probably will give you some suggested problems to work on, perhaps a little bit more in section 2.2, perhaps. Well, maybe 2.1 is enough. I'll take a look at it. But nothing to hand in on Friday. And also, unlike multivariable calculus, no take home, so that's happy, right? Good weekend. Nothing to do on Monday except doing some reading. You can use a note card, front and back, 3x5 note card for the test, and you can use your calculators. Any questions about the procedure? All right, let's spend some time then talking a little physics and a little population modeling. The main kind of physics example we consider in this class is called a harmonic oscillator, also known as a mass on a spring. However, the harmonic oscillator model applies to other situations besides masses on the spring. Okay? If it was only important for masses on the springs, it wouldn't be that big a deal. A harmonic oscillator has other applications besides that. That's just the simplest one to think about. So let's go ahead and think about it. I'm going to go ahead and imagine that I've got a mass attached to a spring that's attached to a ceiling. So here's a spring. Actually, let's imagine not attaching the mass yet. Of course, springs do have mass, but negligible mass, let's say. Negligible mass spring. Then we go ahead and we attach a mass. Attach mass. And when we attach the mass, because of the force of gravity, the mass is going to pull the spring further down. Its old equilibrium position here for the bottom was that. Its new equilibrium position is further down. I'm sort of focused on the location of the connection between the mass and the end of the spring. There's the new equilibrium position. I suppose you could focus on the center of mass if the spring truly is negligible in mass. But let's not worry about it. New equilibrium position. That's a certain distance down from the old equilibrium position. If the old one was, say, right here, there's been a certain displacement that the mass has caused. Hooke's law is the basic law governing this kind of situation. It's not necessarily perfect, especially if your spring breaks, like the block of wood is too massive, causes your spring to break. Then Hooke's law is no longer valid, but it is pretty good for small displacements. It says, well, effectively, the restoring force of the spring like that is proportional to, in this case, the displacement that was caused. I'll call it displacement. Well, I'll just call it displacement here initially. So there's some constant proportionality. I guess I'm focused on the magnitude of the force here. I'm going to go ahead and put double absolute value signs around the force to emphasize magnitude in the way that I do in multivariable calculus. The magnitude of the force is some constant times the displacement. I want to call it displacement y because I'm going to reserve that for something else. There's some constant of proportionality. Therefore, the constant of proportionality is the magnitude of the force divided by the displacement. But the magnitude of the force when the mass has caused the spring to move down is exactly balanced by the force of gravity on this mass. Because it's going to be at this new equilibrium. So those forces have to balance out so that it doesn't move unless you actually stretch it some more. Crunch it. So in fact, this is the same as the magnitude of the force of gravity divided by the displacement as well. What's the magnitude of the force of gravity going to be if the mass of the block of wood is m? 9.8 times m. mg is the typical way to write it. Where g is the acceleration due to gravity, about 9.8 meters per second, every second. 9.8 meters per second squared. So that's how you figure out the k. This is called the spring constant. And it's going to be different for different springs. Let's go ahead and put some numbers in here. Let's assume the mass is 3 kilograms. G is, again, 9.8 meters per second squared. And let's say the displacement that happens when we attach the mass to the spring and let it go down to a new equilibrium is 0.2 meters. Okay, so again, it's got an old equilibrium. I attach a mass to it. It stretches it down a little bit, comes to a new equilibrium. That displacement, let's pretend, is 0.2 meters, 20 centimeters. What? About that one? Something like that. That's going to help us figure out k. This information tells us k is going to be 9.8 meters per second squared times 3 kilograms is, what's the units for that going to be? Right there. Meters per second squared times kilograms is newtons, is the official unit if you didn't know that. Divided by 0.2 meters. 9.8 times 3, if you can't quite tell that. 9.8 times 3, that's what? 29.4. I divide 29.4 by 0.1, I get what? 294. So if I divide it by 0.2, I get half of that. Somebody check my calculations. I made a mistake the other day. 147. 147? 147 newtons per meter. Might make more sense to convert that to newtons per centimeter, but let's just leave it like this. So that's what the spring constant is. As far as describing the motion now, when you grab the mass and say stretch it further and then let go, it's going to oscillate. We need to bring in Newton's second law to do that. Typically written as F equals ma. Let's set up a y-axis here. Pretend that's straight. Positive y-axis going that way. Let's say y equals 0 corresponds to this new equilibrium position. There are two forces acting on the mass. One is definitely gravity. The other is the force due to the spring, the restoring force, again it's called. That's true no matter where the mass is. However, it'll turn out that when it's at this new equilibrium position, you can effectively ignore the force of gravity. It's sort of taken the force of gravity into account. as far as changing the F equals ma equation into a form we can work with, we can ignore gravity at this point, it turns out. You have to prove that, but we can ignore gravity again. Just focus on that restoring force, and that restoring force is proportional to the new displacement. If I take this new equilibrium position and I take this mass and I displace it further, either down here to make y negative or scrunch it this way to make y positive, the force due to the spring is proportional to that displacement, which is now what I'm going to call y. So, let me rearrange the equation. Let me write A as a second derivative. Thinking of y as upward as positive. I could do downward as positive. I chose upward. That's m times A. That's m times the acceleration. What's the force? It's, again, proportional to y. In fact, it's k times y. What direction does it have? It's, let's see, when y is negative, when I pull it down here, the force is in that direction, the opposite direction, the positive direction. And when I scrunch it up here, the force is in the opposite direction, which is the negative direction in that case. It's got the opposite sign as y, is what I'm trying to say. And down, when it's down here, when I pull it down, y is negative. The restoring force is in the positive y direction. When I scrunch it, y is positive, the restoring force is in the negative direction. So I need a negative sign right there. That's what I'm trying to say. That's a differential equation. A second order differential equation. It's got a second derivative in it. I could leave it like that. I could also write it like this. I forgot to say something. I am ignoring friction here in saying the only force we have to consider is the restoring force. I am ignoring friction, I forgot to mention that. Okay? That would be another force going on, but we're ignoring it to keep it as simple as possible. Either of these ways to write it is okay. You can also divide everything by m. You can write it with primes if you like. Any one of those three ways of writing this second order differential equation is fine. You can also say there's a certain initial condition. If you grab the mass from this new equilibrium position and, say, pull it down 0.3 meters, just to make something up, and then let it go from rest, that gives me two initial conditions: an initial position, negative 0.3, and an initial velocity. What would the initial velocity be if I let it go? Zero. I'm not giving it a push or a pull as I let it go. So those would be some initial conditions that would satisfy what I just verbally said. As you know from the reading and the completion assignment, there's other stuff related to this. You can convert this to a first order system. A first order system of differential equations involving y and v, where v is the velocity. And you can draw what are called solution curves in the phase plane. For this kind of model on the test, I'm not going to bother with that stuff. It's very important after the test. But for the test, this is the kind of thinking you need to do for this problem. Okay, we'll leave it there. There is, like I also mentioned, a Predator-Prey problem. Similar to the one on the test from last year. The Predator-Prey model was discussed in the very first section of Chapter 1, and it was also discussed then in the very first section of Chapter 2. Doesn't matter whether you think of X or Y as the predator and prey, X is the predator and Y is the prey. You could do it vice versa. You could do Y as the predator and X is the prey. And so one of the things to do on the test is to identify which variable is which based on the nature of what goes on the right-hand side. If I want, for example, Y to be the predator and X to be the prey, remember the predator eats the prey. If you get confused about that. The predator eats the prey. Write that down if that confused you. They both happen to start with P, which is maybe unfortunate. The predator eats the prey. The predator is going to benefit from interaction with the prey. Leave a little space here if you're writing stuff down. Put a plus sign. There's an XY term to keep things as simple as possible that reflects interactions between X and Y, between the predator and the prey. When X and Y are both large, this is going to be a large quantity, which means it's going to result in perhaps dy dt being large, causing the predator to benefit. There needs to be some sort of coefficient there. Make something up. It's a measure of how beneficial predator-prey interactions are to the predator. But the fact that that's positive means is going to mean this is the predator. With the prey, it's going to be a negative interaction. Maybe -3 times X times Y over there. But the model's not done. These are the interaction terms. We also need terms that reflect the growth of the predator-prey, or maybe the decay, in the absence of the other one. The predator doesn't have anything to eat. That's not good, right? There's no prey. It's not good for the predator or its growth rate. Now, you might say, couldn't the predator have other food? Well, yeah, but let's keep things simple. We're only thinking about these two species, and the predator only eats the prey and nothing else. Keep things simple here. If there's no prey, if X is non-existent, we want the Y to die off. That would make sense because they don't have any food. Maybe -2Y is going to reflect the fact that Y dies off when X is 0. Because when X is 0, this term goes away. And the equation reduces to dy dt equals -2Y, which is an exponential decay. Does that make sense? Now I could just put like a 3x there, and that would be okay. It would be a predator-prey. Saying, well, the prey eats something else, so in the absence of the predator, they flourish. But it's typically more realistic to think about a logistic growth model for that part of the prey's equation. So you might have something like this. Remember, that kind of term would reflect a logistic growth. 10 would be the carrying capacity. You do have to think about units. Units for Y might be hundreds, and units for X might be thousands. So when I say the carrying capacity is 10, I would mean 10,000 in that situation. These coefficients are probably too far from 0 to be realistic, but don't worry about it. Keep things simple. You should also be able to find equilibrium points, as you read about, or should have read about. Which is a bit tricky in general, because you have to solve a system of nonlinear algebraic equations. However, for examples like this, it's definitely doable. You want to set these things equal to 0 and solve the resulting system of algebra equations. Ignore the differential equations for the moment. We're after equilibrium points in the phase plane, just like we've solved in chapter 1 for equilibrium points on a phase line. What values of X and Y in this case make both of these things 0 at the same time, simultaneously? And the key thing is to try to factor as much as possible. And in this kind of example, it's not too hard. These two terms both have an X that can be factored out. They both have a 3 as well. You don't have to factor out the 3, but I will. What's left over after factoring? Well, in this term, the 1 minus x over 10 is left over. In this term, a minus y is left over. Can we factor things out of this one? Yep, common factor of y. Factor it out. Write what's left. And when you write it in this factored form, this system of algebra equations, it's easier to see what the solutions are. Certainly x equals 0, y equals 0 is one solution, the origin. X equals, what would it be? 2/5 is going to make that 0. And if x equals 2/5, I can make this 0 by an appropriate choice of y. Effectively solving this system of equations. This equation is solved by letting x equal 2/5. Plug that into the first equation. You're going to get 1 minus 2/5 over 10 is going to be 2 over 50, or 1 over 25. Y is going to be, put it on the other side, 1 minus 1 over 25, 24 over 25. And that means the point 2/5 comma 24 over 25, if I haven't made any mistakes, try to stay alert and catch any mistakes I might make. That's going to be an equilibrium point, because it solves the system of equations. It makes the right-hand sides both equal to 0, which means those are locations where the derivatives are equal to 0 for the solution function as well, both for its x coordinate and its y coordinate. I haven't talked about this in class really, but you've read about it. You should have read about it. Are there any others? Am I missing any? I am missing one more.
0, 0.
I already mentioned that one. If y is 0, x doesn't have to be 0. It could be 10, yeah. If y is 0, making this one 0, x could be 0, so we get the origin again, or x could make this 0, and if you plug in y equals 0 into there, that means x must be 10. So the other point, the third equilibrium point, is 10, 0. Showing your work in this kind of problem could be done in a couple ways, either doing this factoring and writing down, probably the third one I'd have you find would be this one actually. Writing down the new system of equations and showing that kind of work. Alternatively, you actually could just take these points, x equals 2/5 and y equals 24/5, plug them into the right-hand sides back here and see you get 0 in both cases. You also, finally, if you look back at that problem from last fall, should be able to draw graphs of x and y as functions of t. When you are given a graph of the solution curve in the xy plane. Again, I haven't talked about this in class, so people watching on YouTube don't know about this. I haven't done it in class yet. If they don't have the book. But what's drawn in the xy plane is a solution curve to the system of equations, which is really a parametric curve. Same kind of idea as in multivariable calculus for those of you who took that. X of t comma y of t. What does it look like here? I don't know. I think the one on the exam from last fall looked like this. It's spiraled in toward an equilibrium point. In this case, the equilibrium point would be at 2/5, 24/25. You should be able to take this graph and also draw how x and y depend on t, based on that. It's a little tricky. You should try to match these up vertically with each other. Actually, I think on the exam I have to draw them in the same graph. X and y as functions of t. They're both always having positive values here, at least in this much of the drawing, and that would make sense physically with the model. They oscillate up and down with smaller and smaller oscillations as you go. And x is going to head toward a horizontal asymptote at 2/5, while y heads toward a horizontal asymptote at 24/25. Obviously, the scales on these axes are not the same. X starts out fairly low, less than 2/5, goes up fairly high, doesn't go higher than 24/25, so it doesn't look like it on this scale. X is going to do something like that. Y starts out high, higher than 24/25, goes down, has a minimum right about there, where x is at close to 2/5 there. So if we try to get this accurate, this is the trickiest part. When x comes back down around there, that y reaches its minimum. So something about like this. I could try to match these up better over here too, but I'd be taking another minute or so to do that. So that's something to think about. Make sure you try to do a careful job when you look at last year's exam. I'm not doing a super careful job over there, for sake of time. Okay? You'd want to match up, x has its minimum, or y has its minimum where x is close to 2/5, and its maximum when y is close to, when x is close to 2/5. Y has its minimums when y is close to, or excuse me, x has its minimums for each oscillation when y is close to 24/25, and its maximums for each oscillations when y is also close to 24/25 on the other side of it. I know that went fast. Okay. Spend time looking at last year's exam. Make sure you study that question.
And then the 10-0-1, would you include that on the same solution?
You can, well, it's going to be way over there, so we're only focused on this part of the picture. Okay, that's the part that comes up on the exam, just like last year's exam. Okay, so do a careful job when you practice that. There will be a flow problem on the test. It's like the simpler example here. Let's look at the simpler example again. The one on the test is like this. So in this example, dy dt equals -2y results in a general solution of c times e to the -2t. And the c ends up being the y0, the initial condition. And then I replace the y0 with just a plain y, to ultimately write this formula. Again, there are benefits to this when we get to chapters 3, 4, and 5 especially. This is going to allow us to do some pretty cool things, so it's worthwhile because of that. Okay, that's what I claim at least. Initially, we're just trying to learn about it, and what are we trying to learn about it? We're really trying to learn about how to view it. What this really is a bunch of functions for each value of t. It's a family of functions. Functions of y as t varies. I get infinitely many different functions for the infinitely many different choices I can make for t. It's a linear function of y whose graph goes to the origin, as I've drawn before. The key question we want to know, what you're going to be asked about, is how is it related to the differential equation? And what we typically do is we consider the associated flow maps, which typically, ideally, you pick t equal to 1. That's sort of the simplest one to think about. You consider the time 1 map. In this case, it's that. Remember, the solution, written in terms of an initial value of y, y0, has the same exact formula as up on the screen there, except we replace the y with y0, and we typically put it in front as well. How are these two things related, besides having essentially the same formula? The point is that when your equation is autonomous, iterating this gives you values of that. And that doesn't work when it's non-autonomous. I think I'll try to take 1 minute to show you it doesn't work when it's non-autonomous today. This recursive equation here generates a sequence of values y0, y1, y2, y3, y4, etc. in such a way that for autonomous equations, y sub n is phi sub y0 of n. That phi, not that phi. And the subscript there, I'm talking about the original solution. This works for autonomous. For autonomous, And it works most nicely when your solution doesn't have any vertical asymptotes. Then this will work with picking t equals 1 with the other examples where we have vertical asymptotes. I sometimes have to pick a really small value for t here. And it doesn't work for non-autonomous equations. Again, these things here emphasize that if I use NestList to iterate the flow map at time 1 flow map, or if I use table to find the values of the solution function for different t's, different discrete values of t, that's what table does. Table starts t at 0 and goes up by 1 each time, and so I'm seeing the outputs of the solution here, which match the values of the iterates here. That doesn't work for non-autonomous equations. If I try to use d-sol value, for example, for a non-autonomous equation like t times y on the right-hand side, but you have to do that for Mathematica. So if I try to do this, and if I set that expression equal to phi sub y0, the old phi there, the non-fancy phi, I can do this. Just copy and paste that. I can do that even when it's not autonomous, and I can also do this. Do the fancy phi, t up there. Use the other phi and just replace the y0 with a y, and the t is just a t. Now what happens if I iterate this, if I use NestList on this, it does not match the outputs of the solution function, where this is the solution function here. I'll just go ahead and put this in. The y0 I took to be 10, so I got to replace the y0 with 10. We do not get a match. Okay? You do get a match for the first two, but thereafter you don't get a match. So the iteration of the flow map for non-autonomous equations doesn't satisfy this nice property. And in the reading I called that sometimes the flow property or the group property. And it's related to this equation in the reading. Where that circle there is function composition. That's the key property that works for autonomous equations and not for non-autonomous equations that makes this iteration thing work. Okay? So your test example is pretty simple like that. And here's the key fact that I want you to realize. Can I clarify anything there? By the way, I do have some other code in here called cobweb plot. I call it the cobweb plot. That can be used to create pictures of those staircase things. Actually, let me go back to my original example. This is code that I created when creating my own mathematical function here. It's just showing visually what's happening with the iterates in the way that I tried to draw on the board in class the other day. You put your function that you're iterating there. According to my syntax here, I need x min, x max, y min, y max. Those are just the window that I'm going to make my graph on. A seed in the mirror iterate. The seed is the initial value of y. The iterates is how many iterates you want to go. So I could probably do something like this. Negative 10, 10, in both the x and y direction. Seed of 10, 5 iterates. I get a picture that's showing you kind of what I showed you the other day. Except the other day I started on the horizontal axis here. I started at 10. I went up to the red graph, then over to the 45-degree line, back down to the graph, over, etc. That's showing you the iterates are approaching 0 which is reflecting the fact that on the phase line for this differential equation, this autonomous differential equation right here, the origin is the same. The phase line for that autonomous equation looks like that. That's why those irits are going to 0. Those numbers right here are going to 0. Okay? We'll do this a lot more in chapters 3, 4, and 5 in some pretty neat ways, and I think it'll, if we keep working at it, it'll make good sense. All right, what else? You gotta go fast now with the rest of the stuff. What I've typed on here is just a summary of problem types that I mentioned in the email that are going to be on the exam. In looking at the exam again yesterday, I thought it did look pretty challenging, and it also looked kind of long, even for an hour and 45 minutes. I did do a couple things to modify it to make it a little shorter. Initially with these symbolic algebraic methods, separation of variables, undetermined coefficients, and integrating factors, I was going to have you do initial value problem solutions for all 3 of those, which ends up being more work because you also have to plug in the initial condition and that kind of thing. What I decided is to help you save a little time there is only on one of those it's going to be an initial value problem, and the other 2 are just going to be general solutions. Okay? General solutions and solutions to initial value problems can often be written in slightly different forms, as we've experienced in class. And so don't worry about fully simplifying your answer. As long as you get to a valid answer, it's going to be good enough. That'll save you a little time and hopefully save possible mistakes as well. I'll come back to that in a minute here, but I just want to do a quick summary. I also decided to make one of the problems extra credit as another way to shorten the exam. So one of the problems that was on the list that I sent you is going to be extra credit. I'm not going to say which one, but it's going to be extra credit, so you don't have to do it, only if you have time. Should you do it? There's, again, Euler's method is one problem. So I'm summarizing these. I'm organizing our ideas as symbolic algebraic methods, numerical methods, qualitative / graphical methods. You will have a problem where I give you the slope field. I use Mathematica to make a slope field and put it on the test. And you have to sketch reasonable pictures of the solution curves for various initial conditions. It's hard to do a perfect job. I'm looking for reasonably nice jobs. Okay? Different people could get different looking solution curves slightly and still get full credit because it's hard to do a perfect job. Just do your very best and hopefully it'll be good enough for my eye. Okay? You want to understand how to make slope fields for autonomous equations and the nature, more importantly. You can make them pretty quickly. Remember, you can, when it's autonomous, you can focus on horizontal lines. The slope marks have constant slopes along horizontal lines. So you only need to think about where is f of y positive, negative, and 0. The graph of the right-hand side function helps you draw the slope field and the phase line. Actually, let's just do a purely visual example here. If your f of y function as a function of y, your right-hand side function would look like this. Let's say it looked like that. Could you draw a phase line from that? Yes, you should be able to, and you should also be able to draw a slope field. Let's mark some of these numbers here along the y-axis. Let's say this is -5, 1, and 4. This is not a solution curve. It just helps you draw solution curves. It's a tool. If you're drawing the slope field, then you label the axes t and y. Those values of y are going to correspond to equilibrium solutions. So at -5, +1, and +4, you're going to have equilibrium solutions, constant functions which solve the differential equation. The slope field will be horizontal along those lines, and so effectively you can just draw the horizontal lines. where f of y is negative, solution curves are decreasing, because that's what the differential equation says. Look for functions whose derivatives, whose slopes, at any point are equal to f of the y coordinate at that point. So if the y coordinate is less than -5, dy dt at that point for the solution curve has to be negative. You get slope marks with negative slopes. Between -5 and 1, you have slope marks with positive slopes because f of y is positive, and they're going to be maximized, not exactly, but approximately halfway between -5 and 1. One's up there. Not drawn perfectly by any means here. I should make these flatter. Between -1 and 4, you have negative values for f of y. Above y equals 4, you have negative values for f of y again. A quick sketch of the slope field is like this. A quick sketch of some solution curves. It'll look like this. And on the phase line, if you think of this y-axis as being the phase line, you've got 3 equilibrium points at 4, 1, and -5. Because of the direction of solution curves, the arrows are going down here, up in here, and down there, making -5 a source, +1 a sink, and +4 a node. In terms of that linearization theorem, f prime of -5 is positive, meaning, since f of -5 is 0, that your function goes from negative to positive there, meaning your solution curves are going from decreasing to increasing, and that's why -5 has to be a source. At +1, the derivative of the right-hand side function is negative. Since f of 1 is 0, that means the values of f of y are going to go from positive to negative as y increases through 1. Meaning solutions here are increasing just below 1, and just above 1 they're decreasing, making 1 a sink. The linearization theorem tells you nothing about the equilibrium point at 4, because the slope of the curve there is 0. Doesn't guarantee it's going to be a node. It could be a sink or a source. If you cross the axis like this for your f of y, even though the slope at the crossing point is 0, the values of f of y are still going from negative to positive, and so at that point on the phase line would end up being a source. We're doing in time. 6 minutes here. Bifurcation diagrams. Okay, your example is going to be a quadratic. You should be able to use the quadratic formula to help you find bifurcation points. In general, it's very difficult to find bifurcation values exactly. But with quadratic right-hand sides, it's doable because of the quadratic formula. So you have that. I put the alpha in there. That's a parameter. I call this f sub alpha of y. This is really a family of differential equations, infinitely many of them. Kind of thinking about them all at once by thinking about all their phase lines all at once. And when you draw a bunch of phase lines for different alphas, that's the bifurcation diagram. If I set this equal to 0 and solve for y by using the quadratic formula, I get -14 plus or minus 14 squared, 196, I think that's right. -4, a is 1, c is -3 alpha, in the quadratic formula, so you'd get a plus 12 alpha there. B squared minus 4ac. B squared is 14 squared. Minus 4 times 1 times negative 3 alpha is plus 12 alpha over 2a. This gives you the formulas for the equilibrium points in terms of alpha, as functions of alpha. You can simplify this a bit. You could factor a 4 out of both of those. Should I bother? And cancel with the 2 on the bottom. I guess I will do that. You should check this on your own. Do it in my head here. 196 divided by 4, that's going to be 49. 12 divided by 4 is 3. I think this is right. Can you do that in your head? What's the bifurcation value of alpha?
Negative 49 over 3.
Yeah. When is this 0? 49 plus 3 alpha is 0. When alpha is negative 49 over 3, that's the bifurcation value. When are you going to have 2 equilibrium points that are real numbers? When that's positive, you're going to have 2 distinct real equilibria, which is true if and only if 3 alpha is greater than negative 49, which means alpha itself is greater than negative 49 over 3. So, in the bifurcation diagram, you make the alpha axis horizontal and the y-axis vertical, because you're trying to make a bunch of vertical phase lines for different alphas. Negative 49 over 3 is over here. It's when alpha is bigger than that you're going to have 2. So your sideways parabola is going to open that way. Where is it? When alpha is exactly equal to negative 49 over 3, your one equilibrium point's at negative 7. So if you were going to draw this accurately, it would be down here at negative 7 where the vertex is. Something like this, I'm not bothering, excuse me, I'm not bothering to figure out where the alpha intercept is there, don't worry about it. Something about like that. You actually won't have to draw that on the exam. I'll just say draw the phase line for a value of alpha just less than the bifurcation value, equal to the bifurcation value, and just greater than the bifurcation value. You should also be able to identify sinks and sources. The right-hand side function here is a quadratic with a positive y-squared coefficient, so the graph of the right-hand side function is an upward pointing parabola. Just a second. Did I make a mistake? No. It's an upward pointing parabola, so I think it's going to look like this. And that's going to be a sink, and that's going to be a source. I think. Yeah, that's right.
So we just have to draw 3 phase lines. We don't actually have to.
You don't have to draw the entire bifurcation diagram. No. Just 3 phase lines, just like in the book. That'll make it go quicker. Mathematica code. Make sure you can use manipulate, show, vector plot, and plot to make slope fields with solutions in slope fields that can be animated as the initial condition changes. You do not have to do the extra stuff like plot range and plot style and that kind of stuff. I'm after just a basic graph. Also use desolve or desolve value. I'll let you choose which one you prefer. And there were a few different ways you could use them. I'll let you choose which way you do that. You may not remember that. It is in that second Mathematica homework. There won't be any explicit existence uniqueness problems, but it's implicitly in the background in many problems. In everything we do, when trying to approximate solutions, you better know there are solutions. And uniqueness is useful for knowing distinct solution curves can't cross each other. Probably would be good to spend 1 minute on one of these here. I think, let's look at this one here in class today. Logistic model with harvesting. Let's write it with P. dp dt. The basic logistic model looked like this, where n is the carrying capacity, and k, you could call it a constant of proportionality in a sense, but It's probably better to call it a relative growth rate when p is small. So when p is small, the growth is approximately exponential. Then when p gets larger, then it goes like that for the logistic. You know, typically k might be like 0.04 or 4%. So 4% relative growth per unit time, like per year, when the population is small. The population gets larger, it's no longer valid to think of it that way. That's the basic logistic model. How do you deal with harvesting? In fact, periodic harvesting. Harvesting is like fishing, right? You got a population of fish in a lake, you go out fishing, you allow for the population to be harvested. If it's a periodic thing, you might want to model with a sine or cosine of a certain amplitude, a certain period, and a certain vertical shift to that harvesting. You wouldn't want the harvesting to be negative, so you'd want the subtractor to be always a positive quantity. You can't harvest negative. I guess you could harvest negative by just putting fish in the lake, but we're not thinking about that. So for us, the harvesting is always positive, what's in the parentheses, and then we're subtracting it because we are harvesting. We're taking the fish out. And depending on the units, you might have something like this in there. Maybe the units are millions of fish, and so 0.1 would be 100,000 fish per year. This would be in units of fish per year. 0.2 is an amplitude showing you how high this part can go above that. Ultimately, this expression can get as high as 0.3 and as low as 0.1. If I said the period was, say, half a year, sorry, we're going over here. If I said the period is half a year, that's going to tell me what goes in front of t right there.
Wouldn't this drop as low as negative 0.1?
Yeah, you're right. Thanks. Thanks. Let's make it 0.3. The period, if it was half a year, then you'd want the coefficient of t to be 2 pi over that period, which would simplify to 4 pi. Okay? That would be how a reasonable way to model the harvesting, at least if at time 0, the graph of your harvesting is at its midline, or its average value. The sine graph is going to look something like that over time. So if that was where it starts at time 0, then this would be a reasonable model. Okay? See you on Friday then.